Bismillahir-Rahmanir-Rahim. In this video, I am going to solve the blending linear programming problem, and the problem which I am going to consider in this video is this one, where we have three types of the raw material and two final product we are making using these three raw material types. And against each raw material, we have given some information regarding how much per unit cost we are bearing and what is the total amount available of each raw material. And then these two products we are making, product number one, product number two, and what is the demand of the product one, what is the demand of the product two, and what is the selling price we are taking while we are selling these final products. And furthermore, we have given the minimum proportion of the raw material we are using to making these products. Like raw material one, we must use 40% to produce product number one. Similarly, raw material two, we must use 10% to produce product number one, and so on. Similarly, we have given the maximum proportion, that is basically the maximum raw material we can use to produce product number one is 60%. Similarly, the maximum 20% of the raw material two we can use to produce product number one, and so on. So first of all, we are going to formulate this one. So how we can formulate that one? So the decision variable of this particular problem would be Qij, where I is representing the raw material, J is representing the final product. So the quantity of ith raw material we are using to produce product J, and this is representing the product number one. Okay, so the quantity of the product one we are producing using the raw material 1, 2, and 3, and this is per unit selling price. Similarly, this is product number 2, and this is the selling price against the product number 2, minus, so this is basically the total selling price, minus we are doing the total cost. So how we are calculating the total cost, that is, this is against the raw material 1 total cost, this is against raw material 2 total cost, this is against the raw material 3 total cost. And the constraints we have, one we constraint have the supply, or you can say the capacity constraint, that is this one, which means Q11 plus Q12 must be less than or equal to 2000 available raw material. Q21 plus Q22 must be less than or equal to 1000. Similarly, Q31 plus Q32 must be less than or equal to 500. So these are the capacity constraint, or you can say the supply constraint. And then we have the demand constraint. So this is the demand constraint against product number 1, and this is the demand constraint against product number 2. And then we have the minimum proportion constraint. Okay, so these are the amount which we should use minimum in order to produce product number 1 of the raw materials, and this is for the these are for the product number 2. Similarly, these are the maximum proportion we should use to produce product number 1 while we are using these three types of raw material. So regarding minimum proportion, we have these set of constraints. Okay, so that is, we are saying that in order to produce product number 1, we should use at least 40% of the raw material, or you can say the minimum raw material we should use of raw material 1 we should use is 40% of the total available raw material. Similarly, raw material we should use in product 1 is 10% at least, and so on. And this is regarding the maximum proportion perspective. And we can generalize this model in this way. So this is basically the selling price, this is total cost. So we want to maximize the profit, that is basically the selling price minus cost. This is the supply or the capacity constraint we have seen. We have the demand constraint. This is the minimum proportion of the raw material we are using to produce the product, to produce a particular product. And this is the maximum proportion constraint to produce the final product. Okay, now we are going to implement this model into the OPL CPLEX Studio. So the concept which we will learn how we can create the separate data file, and then how we can read those data files, as well as, because our decision variable is a two-dimensional decision variable due to the indexes I and j, so that's why we'll use two-dimensional array concept. Then we will also discuss how we can perform the post-processing. So what I mean post-processing mean, after solving the model, what we whatever we are doing, that is called as a post-processing in OPL CPLEX. And then we will try to learn the main body, which is basically controlling the flow of the code, right? And in that we will try to learn how we can generate the solution report, and then how we can know that how much time the CPLEX has taken to solve this particular problem, which is called as a computational time. So in order to implement this particular problem in the OPL CPLEX, so let's open the CPLEX Studio, and we will first of all create a new project, file new OPL project. We will write down the name of the project, which is blending linear programming problem, and then we will select the directory where we want to save it, right? And in this particular project, what type of files we are needed? We need to create a model file in which we will write down the code for the problem. Then we need the data file, right, where we will store the data. And we always needed a configuration file in order to run, or you can say in order to solve this particular problem. And then we will also needed a setting file as well, because in order to find out the computational time, like how much time the CPLEX is taking. Especially we want to customize it, because by default CPLEX is giving us the wall time computational time, which was a normal clockwise time. But we want to find out the CPU computational time. So how we can do that? We can basically change the setting while using the setting file. So we need all fours. So click finish. So once we will finish this one, so you can see that we have basically the four files. One is a configuration, another is a model file, another is a OPS, that is basically the setting file, and then we have a data file. So if I click OPS first of all, which is a setting file, and as you can see that on the title we have the mathematical programming, and in general you can see the computational time reporting, because by default it is giving me the wall clock time. That was your computer's clock time. But we want CPU time. So click over CPU time. Now this would be the time we want in our report, right? And now we will go back to our model file, and we will start writing down the code to solve the particular problem. As I have already done this part, so let me show you. That is this one. So basically, let me show you. So this is a model file. So let me show you the problem again. So we have two types of indexes. One is the raw material index, another is a final product index. So this is I and this is J. Final products are the J. So that means first of all we need to define two types of indices. So we define one indices for the raw material and another indices for the final product, right? So that's why we are using a keyword integer int raw material, and three dots are indicating that we will store the data in data file or in Excel or whatever. So right now we are using the data file, so that these three dots will indicate that you have to check the data file for the data of the raw material. And then we are using the data type range in order to indicate that what would be the range of this raw material. So we are using a variable RM is equal to 1 to raw material. So whatever the raw material we will provide, it will start from 1 to that particular value. So how many type of raw material we have? So we have three types of raw material. So that means the range of RM would be 1 to up to 3. Similarly, how many types of final product we have? We have two. We consider the range FM is equal to 1 to 2 dots, right? Remember that for defining the range. Final products, and how many final products we have? We have two. So that is 1, 2. That would be the range. The next thing we need to define is the available data. So we have given the unit cost. The given is the capacity, or you can say the supply against each raw material. The data set given is the demand, and as well as the selling price. the minimum proportions we should use of these raw materials and the maximum proportion. So first of all, let's define the selling price. Selling price against final products. So that's where we are writing down int price FP is equal to 3 dots, and we have defined this data file in a data file because we have the two final products. So that means in an array in data set we must have two values, that is 10 and 8. So that means this is indicating the price against product number 1. This is indicating price against product number 2. Okay, similarly we have the cost, that is a unit cost, that is this one, okay, against 3 raw materials. So that is basically the float type, because we have given the cost in fractional. So that's why I'm using float cost raw material, because there is a 3 types of the raw material. So that's why we have 3 values in our array. So this is basically the unit price against raw material 1, 2, and 3. And then we are using the supply and the demand. So supply against raw material, demand against final product. So similarly, we have 3 supply values and we have 2 demand values. And in the end, we have the minimum proportion of the raw material raw materials, which we are using to produce the product. 1, 2. Similarly, we have the maximum proportion of the raw material 1, 2, 3, which we are using in product 1 and 2. So how we will, so this is a 2-dimensional array, how we will define this data set. So this is basically we are using 2 arrays, okay. So that is basically array inside the array. That is basically, this is indicating the minimum proportion we are using of the raw material to produce product 1 and product 2. This is for product 2. Similarly, this is the minimum proportion of product 2 we are using to produce product 1 and product 2. Similarly for raw material 3. This is for the maximum proportion perspective. So the maximum proportion of the raw material 1 we are using to produce product 1. Similarly, the maximum proportion we should use to produce product 2 of the raw material 1, and so on. Okay, so we have defined the indices, we have defined the parameters. So the next task is to define the decision variable. And the decision variable of ours is the production quantity of raw material I to produce the final product J. So we can define the decision variable D var, that is a key variable which is defined decision variable, okay, which is decision variable. Float plus, that means this quantity must be positive. So due to this positive sign, so we are saying that the quantity must be the positive, and float is indicating that the answer could be occur in a fractional perspective, or the fractional values are possible. Okay, so we have defined the decision variable. Now we are going to calculate the total profit. Okay, so instead of I am simply writing down in a single statement, I am separately calculating the total price and separately calculating the total cost, and then I am subtracting the total price minus total cost. So how we are calculating the total price? That is define expression. So that is D express float total price is equal to sum J in FM for all products. That means we should sum against all products. So price of product 1 multiplied by the that is the sum of the raw material used to produce that particular product. So this is basically the total price we are calculating, and similarly we are calculating the total cost, right? And then we are calculating the profit. So how we can calculate that one? That is total price minus total cost, that is the total profit. So this is our objective function. So we want to maximize our profit. So how we can define this one? So in the model part, we can write down maximize this profit. Subject to, we have the constraint. So first constraint we have, that is a supply constraint. As I told you in my previous videos that it's a good practice to write down the name of the constraint, which we can use in the later stage, especially in the post-processing, if you are interested to find out the sensitivity analysis. Okay, so by the way, so we have the first constraint is a set of the supply constraints, and in a supply constraints, so that is for all I, that means for every raw material. Okay, so that is the for all. I in raw material, some J in FM, that the production quantity must be less than or equal to supply I. So that is this one. Similarly, we need to model this one. That is for all J. So this is for all J, that is demand. Sum against I in the raw material quantity Ij must be equal to the demand. That is this one. So next we are going to implement the minimum proportion constraints for all Ij. So that is basically nested loop. So for all I, that is then for all j. So that means for every ith value, complete this loop whole. Okay, and then for that we are saying that the production quantity must be greater than or equal to the minimum proportion which we have defined earlier. That is this one. Okay, which is basically that is this one. Okay, so the minimum proportion multiplied by the sum of the production quantity that we should use. Similarly, we have the maximum proportion that is less than or equal to. So that is basically the supply constraint, set of demand constraint, minimum proportion, and the maximum proportion. So here we have completed our model code. Now what we want another you can see the set of line of code which is basically in the main body function. What is the main body? Basically the main body will control the flow of the line of code. Okay, so what does that mean? First of all, we want to solve this problem, right? So in order to do that, I am writing down this OPL model. So this is a keyword of the OPL. That is, this OPL model means this current file model which we have written over here. So this automatically know this one. So when we are writing down dot generate, so what it will do, that it means it will solve this problem, right? And in the next line of code, we are saying once you solve it, okay, now check if again CPLEX is a keyword, dot solve is the default function of the OPL. Okay, we are saying if CPLEX is able to solve this problem, do these line of code, mean run these line of code. If CPLEX is not able to solve the solution, then write down this line of code that we couldn't have find the solution. So how we can do that? That is a write line, right? And in double quotes, whatever the message you want to write, you can write down. Okay, let's say CPLEX is able to solve the problem. So the next thing we are doing it, we want to store the solution in a separate file. That is basically the answer report file. So how we can do that? We can use the keyword var and then space of file, right? So that is O file is the name of the variable in which we are storing the answer report, equal new. This is the keyword of ILO OPL output file. So this is a function, and this is a whole path where you want to store the file. So then the answer file name I have given is the answer.txt. So that means this is a text file in which we are going to store the solution. Okay, and remember that make sure that the sign you should use is the front slash instead of the backslash. Otherwise you will get the error. Okay, so make sure you are using the front slash. Okay, so we are saying that output must be stored in the answer.txt file. And then we are saying that in that file, so that is basically this file is once is created, and then we are saying in that particular file, write line. What should OPL write? This model, that means the problem, the model which we have written over here, the print the solution. So whatever the solution they have received, print this in this particular file. The next thing, so when I am solution, talking about the solution, that means I'm talking about the decision variables answer. Okay, so the next thing we want to write in this particular file is that is get the CPLEX time. So which means this line of code must be written as it is, which we have written in the double quotes, comma, then the solver name CPLEX dot. So this is again the by default function of the OPL, get CPLEX time. So what it will report us? It will report us the computational time. So remember, in the setting file, we have changed the computational time from wall time to CPU time. So it will tell us the CPU time, right? And next we are saying, I want to separately write down the total price. That's why I'm writing down this model dot total price. Similarly, I want to write separately the total cost. So it will tell me the total profit, but I am also want to know what is the total price and what is the total cost. So that's why I have created the total price separate. I am calculating it, and total cost separately I am calculating it, right? And then we are saying offline dot close. So close this file. So this line of code must be written, right? And then we are writing down var obj. That is basically the decision variable or variable we are creating. That is obj, and we are storing the objective function value in this particular variable. So get obj. So that is basically the profit value will be stored in this particular variable, and we are printing that profit, okay, while calling that particular variable. Okay, so similarly I'm also writing down the computational time. So this is basically the post processing perspective. Okay, that's why I'm writing down from here. Okay, what does that mean? I will show you in a few seconds. That is this OPL model dot post processing. So when this OPL will read this function, it will go to downside. That means after the main file, it will execute this block of code where we are writing on execute write line. So that means in the solution tab or in a in a script log, we can see that this total price and total cost as well. So in an output file, we can check the solutions, as well as this will also show us the solution in the script log file. Okay, so now I hope you understand all the line of code. Now we are going to solve this problem. So we will drag and drop this model file, as well as the data file, as well as this is good practice to send the setting file as well. And then right click, run this model. So once we run this one, so the first of all, right now CPLEX is running and trying to solve this problem. So we got the solution, and first of all, what we are getting it from the script log, as you can see that the same line of code, the objective function in a post processing. Okay, so the answer of the objective function, and we are writing down in a post processing that solution of CPU time. Okay, so that is a solution of how much second of the CPU time is taken while solving this problem. What's the total price, what's the total cost, and this is a total profit, and these are the CN variables answer. Okay, so we can also get this type of solution in our answer report where you have stored. So this is a answer report. If I double click over here, so you can see that the objective function, okay, this is the decision variable answer, this is a computational time, this is total price, this is total cost. I hope you understand how we can solve the blending linear programming problem and generate the output report using OPL CPLEX solver. Thank you so much.